if all I've mentioned part good news, there's also the bad, the challenges we must face when using LLMs in our daily lives. There's bias, hallucinations, lack of transparency. Particularly, hallucination is content that appears plausible, but is actually false or inaccurate, can be of different types. Can be factual, refers to wrong information, can be structural, apparently correct format, yet containing invented content. So, for example, a code that appears to work, but it's syntactically or logically incorrect. Hallucination can also be contextual, when the model misunderstands the user request and generates irrelevant answers. And from the training, the LLMs can also learn harmful behaviors, so that they can be triggered through well-crafted prompts to generate toxic contents, which can be offensive, discriminatory. They can promote harassment or bullying or violence. They can encourage illegal actions. So now, all such flaws or bugs of LLMs, they are seen as diagnosis that the AI research community often treats as disqualifiers for human likeness. But are LLM flaws really flaws? I mean, let's try to flip the lens for a moment, a sort of mirror to humanity. No? Humans also hallucinate with false memories, urban legends. We are biased as well from a cognitive, cultural, emotional viewpoints, and must make factual errors daily and all contradictory beliefs. So this implies, in my opinion, that maybe what we call errors in machines actually resemblances with human cognition. So the key point is that humans live with these limitations, yet they still produce meaningful, moral, and effective communication. Why should LLMs be excluded from the possibility of mimicking such human traits? So I think that we need to frame it, not just lowering the bar for LLMs, but really examining what being human-like actually means. So the presence of bias, error, and inconsistency is not necessarily evidence failure, but evidence of alignment with the human's imperfect nature. No? Okay, so let me now build on these and explore a few key points related to the following topics. Let's start with the first one, which is human personalities and LLMs. So, why study human personalities? Well, we're nowadays perfectly aware that LLMs are no longer just tools for generating text. They increasingly show human-like behaviors that seem to emerge naturally from massive amounts of trained data. I believe this raises fascinating questions, such as, do these models develop intrinsic personality traits of their own? And how do they change when we deliberately condition them to mimic specific human personalities? So answering these questions, so I understand what are the implications of these emerging and presumably controllable behaviors, with the ultimate goal of building richer, more natural, and safer human-computer interaction. So, to study human personality in LLMs, I believe an essential starting point is to choose a psychological framework of personality. In this regard, the personality tests, MBTI and BFI are well recognized organized and frequently used in different contexts, from academic research to clinical settings. So with this equipment, we can address the following research questions. First, do LLM agents consistently exhibit personality traits according to the given personality test? Second, can LLM agents mimic specific personality traits through prompt-based conditioning? The third one is, do LLM agents improve mimicking capabilities when instructed to act according to specific human roles? Of course, these research questions are supposed to be investigated on some basic question of LLM awareness of the psychological tests have been properly assessed. Let's first briefly recall the two mentioned tests. So the Myers-Briggs type indicator is a set-rank personality assessment questionnaire, which consists of 4 dichotomies, being 16 distinct personalities encompassing strengths and weaknesses and peculiar behaviors of each personality. There's a summary in the table on the right. And the categorical nature of MBTI, where each individual pertains to a unique category, enables us to frame the assessment as a multi-class classification problem, favoring our attention. The Big Five inventory test instead identifies 5 factors: openness, conscientiousness, extraversion, agreeableness, and neuroticism. And so that a personality type can be characterized by varying degrees of such factors. Okay? And so unlike MBTI, DFI measures personality traits on a scale rather than grouping them into binary categories. So how to administer the test of an LLM agent? Each of the 2 tests consists of a set of questions and a set of options as valid answer. The Myers-Briggs provides a set of 60 questions through the 60 personality platform, which is a well-known relevant source for this test. An LLM is so required to answer with an disagreement level rating, which are then evaluated according to the reference, platform reference, in order to associate a model with one MBTI personality. Whereas the BFI test provides a set of 4 questions, and again, an LLM is required to select an answer from different ratings. Okay. So these are prompts forward from the work I'm mentioning. So the first one refers to the question 1, which is the unconditional prompting. The second one is the personality conditional prompting, in which in respective prompts for both tests, we also include a particular personality or a particular personality factor, okay, so to condition the LLM. We also combine human role and personality type when conditioning the LLM. So let's take a look at some results responding to the first research question. On the left of the figure, which corresponds to a very small temperature, LLM agents tend a unimodal distribution of personalities. The dominant type turns out to be extroverted, intuitive, feeling, and personality, which means that the LLM agents in general exhibit an inherent inclination to inspire or provide support to others, and hold themselves accountable when they make mistakes. We can also notice that the prevalence of judging is a constant over all models. Okay, reflecting an inclination toward organization, planning, while extraverted and feeling success are shared by all models, suggesting engagement or empathy. Temperature leads LLM agents to exhibit even greater creativity, though more personal emerge, while previously identified ones change. Some models, however, such as the Lamb family or German or Fritre, are not affected by temperature change. They consistently maintain the ENFJ personality. Considering a BFI test, figure on the right, at the top shows the N. When the temperature is very low, it stands out that no model exhibits a clear single factor. By contrast, the neuroticism tends not to emerge in all models, and the increase in temperature also mostly affects the neurotic. Oh, now, can LLMs be forced to mimic specific personalities? So here we have on the left the average accuracy results on the personality condition of the Myers-Briggs. On the right, the percentage increase of the personality condition and define the test where we expect the unconditional one. So looking at the results for MBTI, we notice that some LLM agents exhibit limited capability in emulating a personality constructed to be conditional, while others can incorporate the conditioning. And similar remarks can be drawn from the summary of the BFI results. As concerns the first research question, integrating personality and role conditioning can, in certain models, enhance Nathan's capacity to replicate human-like personalities, particularly in those agents that had already shown considerable flexibility and adaptability through personality conditioning alone. Okay, well, let's move on to the detection and attribution of AI-generated text. So New Delhi, the capital of India, is a vibrant city that blends rich history with modern development, designed by British architect Indians. It officially became the capital in 1931, etc., etc. Now we are really able to spot if this text was written by human or an AI text generation model. So this relates the problem of detecting if a text is generated by a human or a machine, known as Turing test, and to the problem of authorship attribution, which requires to identify the author, so or source originator or generator. Well, machine-generated text detection has attracted increased attention in recent years. A number of approaches to access it has been proposed, from watermarking to motive detection, classic learning. But each of these approaches suffers from no limitations. And, we can't always watermark text. We don't have always access to models internals for analyzing complexity, for example. And approaches, current approaches of this type of train, a typical train concept model of each possible generation. So, in a study presented at the European Conference on Artificial Intelligence last year, the idea is to develop a fast learning framework leveraging deeply contextualized dense representation of the text to address both the intent and the authorship attribution tasks. So this is a transformer-based pre-trained language model integration into a framework of similarity learning, optimizing contrasted triple loss function to learn deep semantic subspaces. So the goal is to maximize the cohesiveness of groups of similar text and groups of dissimilar text for downstream classification tasks. So key advantages for this approach, named UseAI, regards applicability, versatility and scalability. Because there's no need to edit text or accessing models internals. We can, in principle, use any pre-trained language model at the core of the learning framework. There's no need to train a separate model for each potential text generation. And so this is an overview of the AI framework, but let's take a closer look at some of its components. So we are given both human written text and machine-generated text documents, which provide selection module that affect the PLM to learn, contextual representations or embeddings. Okay? And by using a loss function, then minimize the distance between an anchor and a positive list, both having the same category, and maximize the distance between the anchor and the negative, different category. Then embeddings corresponding to the same author are grouped together, while those for different authors are separated. So the similarity representation space, enhance the model's ability to learn, primitive decision boundary for classifying the existing text. So therefore, given a new text, its embedding is compared with the Stenchonian embeddings and assigned it to the nearest one. The UseAI framework was evaluated on the well-known invention benchmark dataset, which consists of 200,000 news articles, 19 different AI generation models. Basically, the articles were used to prompt the models to generate a certain number of articles. So just a quick look at the results from the tests by UseAI, which are really impressive. 99% of F1 outperforming all competitors, with also outcome of the learned similarity space for both machine-generated text and human-generated, human-written text. Have the colored ones. And this separation is even more in the auto-classification task, where we can clearly distinguish the subspaces, each corresponding to a particular machine generator, okay, each corresponding to a particular color here in the figure. A final remark, there's a novel benchmark called Open to Image, which has been recently released and will be presented at upcoming NIT conference. Moving to the last topic, changes in moral values through AI-based text manipulation. Well, morality, one that underpins much of human communication, because it shapes our laws, our values, our identities. But what happens when machines start generating language that reflects, distorts, or even manipulates moral values? So in this regard, a few studies have explored morality-based tasks in LLMs, but there remains a gap in how moral values are communicated through language that undergoes revision or editing these models. So that work recently presented at this year's ACL conference that aims to address this gap by posing a central question. how do generative LLMs influence moral expressions when modifying human written content? More specifically, the work tackles four questions. Do LLMs even understand morality in the psychological sense? Then, how does simple editing alter moral content? How do models behave when explicitly acted to strengthen or weaken moral tones? Either generally without particular condition or when conditioning a model with respect to specific moral dimensions, like fairness or care. To address these questions, we need to ground our analysis in a social psychological framework of human morality, like the moral foundations theory, which breaks morality into 5 dichotomous dimensions. And this axis allows to systematically measure and interpret how morality is expressed or altered by LLMs. So our methodology includes revision, rewriting, to consider revision, rewriting, and continuation text modification tasks. The methodology also includes involving 5 human annotated datasets, a selection of open source LLMs, varying by sizes and detaches, 4 models for moral foundation prediction, and assessment criteria to measure magnitude and shift in relative importance of the moral Let me give you a necessarily complete summary of the results. So, for the moral unconditional manipulation of text, models generally preserve the original tone or absence of moral tone when asked for revision or rewrite. The top of the figure on the right shows 2 examples. This thing when continuing text, as shown in the bottom, LLMs often amplify multiple moral dimensions, not just the most salient one. So these may indicate overgeneralization of overcompensation. We thought to emphasize moral content models reliably did so, but even introducing moral tones into neutral tests. And this shows a certain capacity to moralize and moralize, so raising questions, of course, about potential bias and rejection during generation. The continuous setting has the greatest impact on altering moral expressions. Then, when asking the model to specifically increase or decrease expression in a targeted moral domain, we generally observe lower values compared to C and moral blind conditioning, and this is actually expected since prompting the model to alter expressions related to specific moral dimension when the trial is diminished, then leads to localized changes. Okay, moving to the conclusion. So at the end of this brief talk, I'd like to open for an alternative, maybe provoking perspective, as we might ask ourselves, what if we look differently at LLMs? Instead of seeing them only as a systems to critique or regulate, we could leverage the human-like parents as a means to learn about ourselves, so as to explore our cognitive glitches, ethical blind spots, and moral intuitions in new ways. Indeed, LLMs are not just tools, they can act as mirrors, reflecting our patterns and amplifiers, revealing the subtleties of affect, morality, communication. So from them we can observe how human values and reasoning emerge. And by studying how LLMs reason, empathize, and even make errors, maybe we get deeper insight into the mechanism of human cognition, emotion, and ethics. In this sense, LLMs facilitate us, they help us understand ourselves better.
Thank you, Professor Tagareli, for that thought-provoking session exploring the cognitive and moral dimensions of AI. Your insights have opened new perspectives on how machines can simulate human emotions and ethics. Due to the slight
Thanks
delay,
to you. Sorry?
Due to the slight delay after the tea break, we missed on Professor Tagareli's introduction, which I would like to continue now. So our keynote speaker, Dr. Andrea Tagarelli, is an associate professor at the University of Calabria, Italy. Dr. Tagarelli is a renowned researcher and the scientific coordinator of the Artificial Intelligence and Data Science Lab at the University of Calabria. He holds a PhD in computer and systems engineering and has collaborated with the University of Minnesota, USA, working in the famous George Carapace data mining lab. His research interests include machine learning, data mining, natural language processing, network science, and information retrieval, and he has authored over 180 peer-reviewed publications. Dr. Tagareli is an associate editor of leading journals such as Artificial Intelligence Review, AI and Ethics, and Computational Intelligence. He is also the founding member of 3 AI-based startups, Juris AI SRL, Big Tech SRL, and ITHEA SRL, bridging research, industry, and innovation. Today, Dr. Tagareli spoke on the fascinating topic, minds, morals, and mimicry, probing language models, human-like affective abilities. Ladies and gentlemen, I would request you all for a round of applause for Dr. Tagareli.
Thank you much for this kind invitation and also for the generous introduction and all for giving me the opportunity to talk with that.
Thank you so much, sir. Thank you so much for your insightful session.
Thank you.
We will now move to the final keynote session of the day 3. We are delighted to conclude our keynote series today with a visionary engineer whose pioneering work bridges aerospace and artificial intelligence. Our next keynote speaker is Mr. George Kolipillai, Chief Engineer Aerospace, Honeywell Technology Solutions Lab. Mr. Kolipillai has played a vital role in advancing aerospace electronics, systems software validation, and avionics innovation. Mr. Kolipillai holds patents and trade secrets in avionics design and has led development for aircraft navigation and guidance systems. Prior to Honeywell, he was a scientist at Aeronautical Development Agency, contributing to India's Light Combat Aircraft program, and also served at Hindustan Aeronautics Limited in the fields of navigation and attack systems. Mr. Kolipillai is an INCOSE certified Expert Systems Engineering Professional, ESEP. He holds a BE Honours in Electronics and Communication Engineering and an MTech in Engineering from IIT Madras. He has led major projects such as Honeywell's GPS-based landing system at Chennai Airport and the customization of inertial navigation systems for India's PINAKA, Pinaka, and Akash missiles, as well as the Advanced Towed Artillery Gun System, ATAGS. Today, he will be delivering his keynote address on the topic AI in Cockpit for Autonomy. Please join me in welcoming Dr. George Kolipillai with a round of applause.
Thank you. Thanks for the nice introduction. Yeah. So, the last presentation, try to make it fast so I don't stand between the final celebration and the lunch. So I'll try to run through the slides quickly. So AI in cockpit for autonomy is the topic that I wanted to talk today. So the agenda is going to be a little overview, couple of minutes overview on Honeywell. That's our company. And then why autonomy in aerospace? What is the difference between automation and autonomy? What is it we are talking about? Why is it needed? Right? And then what's the roadmap for autonomy in aerospace? So we have talked about driverless cars. So where are we heading to when it comes to aerospace? So that's what I wanted to talk on. And then the 4 pillars of autonomy, that's going to enable the automation, autonomy in the aircrafts. And finally the conclusion. Right. So Honeywell, it's a large company, international presence across the world. So more than 1 lakh employees across the world globally. And then so we at India, so there are a lot of projects Honeywell has been involved in and helping the country for almost 9 decades now. Right, so a couple of projects that were mentioned. Honeywell's engine that powers the Indian aircrafts, the defense aircrafts, and we talked about the introduction. Talked about the GPS-based landing system that can increase the capacity of an airport. Right, so if you take so airports like Delhi or Mumbai or Chennai, for that matter, there's very limited scope for expanding the airport. So you can have runways, but the traditional landing systems require a lot of area, right? So that's not possible. So to make it happen, Honeywell has innovated some system called GPS-based landing system that doesn't need that real estate. Easier to add more runways and then ease the landing and takeoffs. So there are many technologies Honeywell is involved in India. And then there are 3 important areas where Honeywell innovates, and then all our products are associated with these technologies. Controls and autonomy. Autonomy is what we will talk about today. Digital transformation and energy transformation. So we all talk about saving the planet for the next generation, right? That's a very critical aspect. So Honeywell is focused on transforming the world and then bring up technologies and products. So in these areas. So now, so let me just jump into the topic that we wanted to discuss today. So it is the autonomy in autonomous flights. So how is the evolution has happened? So we all know when the people started flying, pilots started flying the planes, many of the technologies that we today see did not exist, right? So it used to be just a pilot getting in, flying, looking at the situation around or the terrain, known landmarks, and then flying the plane. So it used to be difficult. So the flights were possible only in a clean, or I would say clear weather, where there is good visibility. So the pilot can see the landmarks. So slowly the aircrafts were started being used for various applications. It became essential from mail service to maybe wars. So the aircraft application was in multiple fields. So there was a need for flying the plane in all conditions, in the night conditions or in a tough weather conditions. There were 5 people required in the cockpit those days. So your pilot, your co-pilot, your flight engineer who will monitor the equipments and see whether every system is good, a navigator who would sit with a big map and then keep noting down where the aircraft is flying, and a radio operator. Once the radios came in, someone has to tune and then talk. So there used to be 5 people in the cockpit. Can you imagine So it's very difficult to think of those days, right? So even in our lifetime itself, I see the technology is transforming the life so much, so much. And so we can't, if you look back, no, maybe 40 years before when we lived a life, it's no more that life we are living today, right? So technology has transformed. So slowly the automation came in. No, so the crude computers, the early computers, they started automating some of the operations. We started getting people out of the cockpit. So it became four. So no more you need a radio operator. The systems automatically tune, and then slowly we said, oh, navigator is not required. We have a flight management computer. We have all automation. No nice systems in cockpit. So we don't need a navigator anymore. Like no, we have a GPS map while driving. So, and then slowly now we came to a now state where we need a pilot and a co-pilot. Pretty much everything else is automated. So that means the cockpit today is highly automated. No, pretty much fully automated. So a pilot in a long haul can just sit and sleep. So you just put it to altitude hold or one of the modes of autopilot. The aircraft is flying on its own. The pilot can rest. So pilot is required to handle the emergencies or the takeoff, landing, or when there is a difficult weather or a traffic. That's when the pilot is required. So pretty much the cockpit is now automated, right? So we only have a pilot and co-pilot now. Why do we need more, right? So why do we need more? But we are talking about from the high end of automation, we are talking about autonomy. Right now we are talking about autonomy. So slowly can we take one pilot out? Single pilot. So it's very scary. 10 years before I was in a conference when we were discussing this. Most of them said, I will not fly an aircraft where now it will go with one pilot. What happens if the pilot gets a heart attack? Right? So now, today we are talking, we have reached a state that we are talking about single pilot operations. And little beyond, we are talking about collaborative free flights. Right? Can the aircraft fly on their own collaboratively? That someone monitors from the ground is far out, right? So slowly the automation has reduced the pilot load, taken over the work from the pilot. We are looking at going beyond totally autonomous flight. That's what we are talking today. So why is it required? First thing, no? So is it not enough? So it is never enough, right? So I remember there was when I used to work in HAL in near Lucknow. So those days the flight fares were so phenomenally high, but our salaries used to be less. No? So maybe 3 months salary I can buy one-way flight. Today with 1 month, a fresh engineer can buy maybe 5 tickets, with first month salary, right? If gets a good deal. So people have started flying. The airports have now all cities, next level of cities are connected. So we have increased traffic. There is more need for pilots, right? So there are more flights. India is one of the country that has ordered large number of aircrafts because so our population, our country needs more connectivity. So there's need of pilots, but the regulatory are not ready to reduce the demands on the pilot training. Maybe you need to have 1,500 hours of flying before you become a commercial pilot. So that's a lot. You cannot just like that pass out and then become a pilot. So there is a shortage of pilot, and there is a increased air travel. You need more pilots. So if our airlines order some few hundred flights in a year, and you need that many, maybe few hundred into 2 pilots. So you need more pilots. That's not that's a shortage. Scalability. So we are talking about now large number of unmanned aircrafts, right? Today, so we are living a life, right? So maybe in Bangalore to reach the airport, to catch a flight, I have to leave some 3-4 hours early. Now slowly we are talking about urban air mobility, where we would be just flying in 15 minutes. But you would see lot of unmanned crafts has to fly or manned. If it is to be manned, you need lot of pilots, right? So there is going to be lot of traffic increasing. something like a Star Wars, what you see, maybe 20, 30 years down the line, you would have the EAMs flying, right? So you need you have to scale up the infrastructure and the safety itself. So if you see, I put one case here, A321 pilot in Europe. So maybe the captain was outside the cockpit, so so he had a medical condition, so he became incapacitated. So he's operating something without his conscience. So how do you handle such a scenario? The pilot had to enter into the cockpit forcefully. So there are cases that we have seen in the newspaper. Ethiopian pilots, they slept off while flying. The aircraft overshot where the airport where it has to land. So these are safety conditions. A lot of scenarios. So can we bring intelligence to manage these safety scenarios? So we need the intelligence. We need more intelligence coming into the cockpit that can address these kind of scenarios, right? And training, as I said, there are large demand for pilots. How do we train all of them? So you need intelligence that can take maybe a place of a pilot and then fly the plane. So now, what's the difference between automation and autonomy? I will make it quick. So the decision making. In the past, what the systems do, they collect information, maybe draw some inference and tell pilot, so here is a scenario, but they don't take decision. They give information to the pilot, make it easy for him to take a decision. So a number of cases we can say, so Mangalore accidents, so pilot got information, but it is now the pilot has to take a decision in a split of a second, whether to land, park, or do a missed approach, right? It's a split of a second. But if you have systems that can have more intelligence and take a better decision, looking at if I take this decision, what is going to happen? Then our systems can become more intelligent and increase the safety, right? The decision making. I'm just taking one example. There could be a number of cases where you can take intelligent decision, right? Rather than helping pilot. So the intelligent system can take decisions. Human involvement. So as I said, most of the time, the systems just give information and pilot is monitoring. So it may say, oh, there is a fault, engine fault. So then it is up to the pilot to understand and then take a decision. So while flying, there could be a case where there's a bad weather. So the system can alert, there's a bad weather, here are the bad weather. So the pilot who takes a decision how to deviate and then go. Just think if the systems become more intelligent and keep the pilot away, take safe decisions. So involvement of pilot is reduced, pilot can focus on better things, right? So that's the autonomy that we are talking about. Finally, the scope of operations. So they are limited today. The automation is limited. So you can give a small function to one of the automation feature that will keep doing. So pilot keeps overseeing. But can we totally offload an intelligent function to AI-based intelligence? That is what is autonomy about. So this, the intelligence, the feature in this avionics can do that function completely rather than just doing some discrete activities that are assigned. So now the roadmap to autonomy. So we know the olden days there used to be dials and scales. So there used to be a lot of dials and then meters that pilot used to see and then fly safely. Slowly it became a very intelligent cockpit where you have a nice dashboard, displays, all controls are brought into the display. So pilot's workload is reduced. So intuitively, so the equipment manufacturers like Honeywell, along with the regulatory and other organizations, continuously work on improving the pilot operations in the cockpit, so we can make the life easier for the pilot to make the decisions, right? That's how it is going. In the near term, So it is becoming more and more automated. So the functionality that used to be discretely done, so they are all integrated. So the pilot can get the information easily. Going forward, so pilot and intelligent machine collaboration is what we are talking about. So now the the functions are helping the pilot. Now, can these functions collaborate with the pilot? First, they assist the pilot, then maybe they perform a function that is delegated to that AI, intelligent system. So it can handle it on its own, but still pilot can override. At the end, we are now looking at an area where the AI can straight away become a pilot. So pilot focuses on some work, AI does another work on its own, and slowly maybe we are looking at an area or a time when AI can fly the aircraft on its own, collaborating. So if you look at here, today we are in I would say the other end of automation. Today I would say we are at the other end of automation. But from here, the next step is what we are talking about. So there's a lot of fear, there's a lot of concern, right? So when I worked on the Jaguar aircraft, Mirage aircraft, Indian LCA, and many pilot commercial aircrafts. So how do we test and validate the system? So we know what the system has to do, we implement it, and exactly we create the scenario and then see how the system behaves. But today we are talking about intelligent system where it is not predictable, isn't it? So I cannot say if I give this scenario input, this is how the system would behave. So that is the concern. So now the companies are working together. How do we bring intelligence, giving confidence on the system and then confidence on the functionality? Same level of safety confidence. So I cannot say just because I brought the intelligent system into the cockpit, so I'm allowed to crash more aircrafts. Can we? We cannot, right? So I cannot say my probability of meeting with an accident or falling from the sky can increase. It cannot. The systems, we have to give high confidence on the system. No? Even if we bring this intelligent system, that is what we are talking about. So the regulatory is now kind of working together in stages. First, so we split that functionality into three. Can we bring intelligent systems into the cockpit in three phases? The first phase is to assist the pilot. So the pilot still is in control. Now the systems gather information, draw inferences, and provide pilot for intelligent decision making. Second stage, collaboration. So the pilot does an operation, delegate an operation to the intelligence system. So when the collaboration, the intelligence system does its job and still pilot can override. But the pilot's workload is considerably reduced. And the last, we are talking about AI becoming a pilot. Right? So slowly we would get into a stage where we have high confidence on the AI system or the intelligence system, not straight away bringing into the cockpit. So the regulatory and all the organizations, related organizations are working on worldwide. There are research and development of standards are going on. How do we bring the first level of AI? So we now split it into from 3 to 6. So it's going to come in stages. So as I said, first reduce the crew operations, help pilot, by bringing a lot of information and inferences. Second, slowly take over from the pilot. So you have one pilot in cockpit, other one can rest, or the other one the AI manages. And slowly you come to a stage where AI flies and somebody monitors from the ground. So that's why in stages, that's how stages it is going. And over a period of time, we would get a place where we will have autonomous flights that can fly on its own. So what is required? We need to have good sensors, data is important for intelligence system, right? Without data you cannot do anything. Data is important. So you need to have good senses, data available, and then maybe a good perception, thinking capability, intelligence. What a man does, the machine has to do. And slowly the decision making. Once you know what is happening, understand the scenario, how do you make a decision? And then control and communication. So these are the pillars of autonomy. Once we get there, the flights will become autonomous. So I just put one slide on sensors. So we call it as C. You should have good visibility to the situation around, situation awareness. So if you have a radar that gives you information about the bad weather, you can get work on it. You can build an intelligent system based on that information. So recently you might have seen one of our aircraft was flying near Kashmir. There was a bad weather. We got into a bad weather, and then we could not get into the neighbor country to avoid the bad weather. So finally we landed with a nose broken, right? Very recent incident, right? So but you just think of a case where the sensor can give information upfront, and then intelligence, the AI based intelligence system can think which is the best way to avoid this bad weather. The bad weather can go tens of kilometers, right, from one end to the other end. Thunderstorm can range from few kilometers, tens of kilometers, or 100 kilometers. But the eye of the thunderstorm is the most important thing. You avoid the eye of the thunderstorm. But if you don't have that intelligence, maybe you would try to take a large deviation, burn more fuel, get into others' territory, or you take an inefficient way, right? So we are talking about sensors that will provide information. That's the first step. So Honeywell makes weather radar. In the traditionally, what pilot does, he do a 2D scanning. So you take a range and elevation, and then you scan, and then keep on scanning and gather all that information, and then make a decision. Okay, I have a bad weather here, I have bad weather here, maybe I would go through this way. Instead, now what Honeywell radar does, it scans everything and then creates a 3D weather buffer. Right? Now entire weather scenario is available to you. It's up to you to build an intelligent system that can decipher which is the best way to avoid this weather. Right? That is what we are talking about. We are talking about sensors that are intelligent. You can say, landing gear. So when to change a landing gear, or when to change engine. There are times that engines have come off during the flight. It would not have come off in a single day. There might have been some vibration, different vibration as it got loose. If the data can be gathered, the vibration data can be gathered, AI model can be run on board, maybe you come to know well in advance, right? So there are many functions that can be enabled. The first step is to get data. So here put a navigation sensor. So today, as I said, when we started flying, it used to be a navigation chart. On that they note and go. Today we rely on GPS a lot. Without GPS, it's difficult to fly. But we got into a situation where GPS can be spoofed, GPS can be jammed. So the sensor now has a difficulty. So how do we make the data navigation reliable? So the companies are coming out with very innovative navigation technologies. So I put some of them. So Honeywell is developing something called magnetic anomaly detection or gravitational anomaly detection or star tracking. One of the technique that leverages AI is vision-based navigation. So you can take pictures of the terrain and decipher where you are. So in overall, if GPS is spoofed or GPS is jammed, you need to have an alternate. Then only you can talk about autonomous flight, right? If you don't have data, if you don't have situation awareness, you cannot talk about autonomous flights. So that's the first step. C, you need to have situation awareness. The second one, thinking. So I put some scenarios here. So there are n number of things we can do. So many a times we say the aircraft, kind of overshot the runway and then crashed. Right? Many incidents we see, or we say the aircraft got into turbulence and then everything fell off, and some people were injured. You might have read. And recently, if you see in the US, there was an accident. A helicopter and an aircraft got into the path. So just think, if you had enough today, it is not that we don't have sensors. They all detect and communicate to the pilot. So in that case, that aircraft and helicopter, when they collided, the investigations, kind of preliminary investigations say there was a communication, but somebody pressed the press to talk button at the wrong time or at that time. So some of the communication was lost. Just think, we had intelligence, the intelligent machines can take control of the aircrafts and then avoid the collision, right? Today, it's all automated. But if it goes into thinking and avoiding, so this is the weather information I put here. So if we can think of systems that can think, pick up the best route and avoid, that can lead to autonomy. So at every phases of flight, we need data, we need situation awareness, we need intelligence that can think and make decision. So while takeoff, there's a lot of intelligence required, right? It's all around pilot today. So what is the speed at which you should take off, or whether the conditions are not good, whether to abort or continue to accelerate and take off. All the fraction of second decisions have to be taken. But that you need to have enough information about the wind, about the thrust, about the remaining length of the runway. If you have all the information, the intelligent machine can make a better decision or help pilot to make an informed decision, right? So at every phases of flight, you have opportunity to bring in intelligence that will lead to autonomous. So oftentimes we would read in the newspaper, an aircraft took a wrong turn, or an aircraft got into a flight level where there was another aircraft. Maybe TCAS went off and then it avoided. There were some mid-air collisions as well. But if intelligent systems come in and take these information and understand what is the best decision to take, then it can lead to autonomy, right? So, as I run out of time, I will conclude. So in short, what I am trying to say, so the regulatory and equipment manufacturers like Honeywell and OEMs like Boeing, Airbus, we are all working on how do we bring in autonomous flights, right? So today, as I said, it is divided into 6. Now we say 1 to 3, then we say 1A, 1B, 2A, 2B, 3A, 3B. So the first stage, we want to bring in pilot assist technologies that can help pilot make a better decision, right? Still pilot has to take a decision. So this is one of the Honeywell-led project for CESA. So what it is focusing on, if you have to bring in, say you are to take one pilot off, single pilot operation, that's the first step, right? So it is focusing on 3 things. First, can the single pilot manage the whole thing, right? Today there are 2 pilots. So one would say, okay, you take care of the thrust lever, I'll take care of the stick. If you take one pilot off, can the one pilot, the remaining pilot, take care of everything? That means systems have to be automated. It has to become intelligent. So the pilot workload is reduced. That's the first thing. Second thing, as the pilot flies, the next pilot looks and monitors everything. So that's why one say, oh, this switch is off, that switch is no. So they figure out, oh, why is this, right? So the second pilot monitors. If you have only one pilot, what would you do? You need to have a system on which you would depend on, you can rely on to monitor the entire cockpit. As one pilot is flying, you have to monitor the whole thing, right? The third thing, if something happens to that pilot, the single pilot, the AI should be able to fly, right? These are the three focuses, and there's a lot of research going on. There's a lot of discussion going on, regulation coming in. How do we increase the confidence on the intelligent machines? And it opens up plenty of opportunities. That's what I wanted to talk about. There are areas where we have to develop AI. More than that, the important thing is how do we give confidence on the intelligence. So what tests we do? How do we give the same confidence on the development methodology? So earlier it was easy to say, give input A, B, C and expect output D. It's no more the case, right? You are now looking at an aircraft coming in. Your AI is supposed to say whether it's an aircraft or something. Suddenly a bird flies and say there's an aircraft coming. You are gone, right? So you are catching up a bird and then saying it's an aircraft. No. So that confidence on the intelligence system has to be increased. So then only it can slowly come into the cockpit. So we can never say because I want to bring in intelligence, I can compromise on safety. No, never. So we are trying to introduce first pilot assist technologies, something like pilot state monitoring. So it's easy. I took some examples. A pilot slept over and overshot. Maybe he got into other aircraft path. So can it be monitored? Today there are challenges. Multiple sensors have to be required to bring that one technology. Second technology, the pilot would be tuning to an airport while landing. I said a lot of things are kind of automated. Still the voice communication is still there. Can AI take bring in speech recognition and say, hey, system, tune to Delhi, run with one. So, how easy it is. So just think when you are driving on a highway at 120, 130, and then you have to call home. So you cannot take your eyes off, right? You will just say, Sri, call home. How easy it is. You can still focus on your work. That's the technology we are talking about. So there are plenty of, at every stage, we can bring intelligence slowly and steadily, increase the confidence on the intelligence system, and make this transition happen from today's world to an autonomous flight. So that would take us there. So that's all I have.
Thank you, sir, for an outstanding and insightful address highlighting how artificial intelligence is revolutionizing aerospace systems and autonomy. With this, we move on to the valedictory session.
Vaidyanathan sir to kindly felicitate our keynote speaker Mr. George Koil Pillai, Chief Engineer, Aerospace Honeywell Technological Solutions Lab. Thank you, sir. The valedictory session will start within 10 minutes.